Continue chapter 13 here. Can we talk about resonance structures? Two or more equivalent Lewis structures. The important thing is never move the atoms, only move the electrons. The resonance hybrid is just kind of an average of the two structures. More or less. Isomers are a different topic altogether, so we left off talking about that. All right, when we draw Lewis structures, we don't really care about the geometry. We don't pay attention to the angles and this or that type of stuff, unless we want to know the three-dimensional structure. If we want to know the three-dimensional structure of these, we can use Lewis structures to tell us what the geometry of this molecule or ion might be. And the way we use Lewis structures is by a valence shell electron pair repulsion theory, or VSEPR. So what VSEPR is just a way to get a gauge of what the 3D geometry is like. And so if we're using VSEPR, then we draw the Lewis structure totally different. Normally with Lewis structures, you don't care, what the proper angle is or what the proper positions are. But for us here, when we pay attention to this, we want to know the 3D structure. In order to know the 3D structure of a molecule, you need to know the bond lengths. That is, bond length is the distance between the center of the atoms. It's the bond length. And the angles. And so if we know the bond length and the bond angles, then we have the 3D picture of it. All right, so we're going to use VSEPR, and this is a whole bunch of talk about VSEPR. We'll talk about VSEPR individually as we go along, so I'm going to skip most of the stuff on this slide. There's too much stuff on this slide. VSEPR deals with repulsions because each group of electrons is negative charge density. And so, Coulomb's law says like charges repel. So if I have a group of electrons here, let's say a single bond here and a single bond here, a group of electrons, it need not be a single bond because there are other groups of electrons, like double bond would be considered a group, a triple bond. So I could have a triple bond here and a single bond here. Or even a lone pair. Lone pair is negatively charged too. But if I have two groups, any two groups of electrons, they're going to try to get as far apart from each other as possible. And so to maximize the distance between the two groups, it'll adopt a geometry. And the geometry here is what we call the electron pair geometry. Pair is a misnomer because it doesn't have to be a pair. Sometimes a group is a pair, sometimes it's two pairs, sometimes it's three pair. But we should say the electron group geometry. So a lot of people change this to electron group geometry, which is actually a pretty good idea. And so if we have two groups, they'll want to adopt a linear geometry that will maximize the distance between the groups. If I have three groups, in order to maximize the distance, they'll adopt a trigonal planar arrangement. And we can see the maximum angle between the three groups will be 120 degrees here. 180 degrees will be here, but if you put a third group, it's going to push these other two groups down. If we have four groups, now this is hard to visualize in 3 dimensions, but if we have four groups, it adopts this. Do you know what shape this is? Well, they call this a tetrahedral face. Tetrahedrons are four-sided polygons. And we get a four-sided polygon by connecting if we connect these points here with lines, that makes a four-sided polygon, which we'd call a tetrahedron. So let's see what a tetrahedron looks like. Here. Let's see if you can see the tetrahedron. It's a rotating model. Oh, I thought it was a rotating model. Maybe not. click here for rotating all. That's a tetrahedron there, four-sided polygon. Here. And then four sides. All the sides are equivalent, and so they're exactly the same. Well, the tetrahedron is going to come from again, connecting the points here. Line. But anyway, that's four groups. Now, four groups, this is going to have the maximum angle between groups. And so if you pick any two, what's the angle? 109.5. So let's pick this one and this one, 109.5. If we pick this one and this one, what's the angle? Yeah, in fact, any two, even the back two, even though it doesn't look like it because it looks a lot wider, if I pick this one on the right and this one on the left, the angle is 109.5. We're always looking at the minimum angle, you know, not the maximum angle. Maximum angle is like this, minimum angle is like that. So the minimum angle is 109.5. And so this has very unusual symmetry. There's no top, there's no bottom. This is called spherical symmetry. It's like a ball. You know, in fact, if you were inside a ball, this would be stable, you know. If you adopted tetrahedral geometry inside a ball, it would be stable. One leg forward, one leg back, and then your arms up. If you're inside a sphere, tetrahedral geometry is really important, and so much so that we want to get very good at drawing these. And it's hard to draw it, and you know, this is kind of the shadow drawing, but normally we don't do shadow drawing. If I want to draw tetrahedral geometry of groups around A, let's say, I would draw one like this. Let's say I have single bonds. So one would go up like this, so it'd just be a normal line. One would go down like this. And so these two would just be standard lines. However, what we'll do with this one, it cannot be in the same plane. So what we're going to do is we're going to dash wedge it out and down, down and out like that. And the other one, we're going to dash wedge it coming out of the board. So this one's coming out of the board like this. This one's going into the board. And so this is the way we draw tetrahedral style geometry. And all the angles are 109.5 on paper. And so you'll have to practice drawing that. You can get good at it. All right, these are electrical repulsions. You can kind of think of them as balloons here. This is a balloon analogy. So if we have two balloons and we want to get the balloons as far apart as possible, this adopts the EPG, electron pair geometry, or electron geometry, EG. I call these EG, electron geometry, or EGG, electron group geometry. And so I just say electron geometry. The electron geometry is linear. So EG, linear, two balloons. With three balloons, obviously three balloons, the third balloon's going to come in here. The third balloon comes in here, it's going to push these two balloons down, obviously. And so what type of geometry will it adopt? What do we call that geometry? Trigonal planar. Planar, P with two A's, double A, planar. Planar. A trigonal planar. Bond angle, this is not right. This is the angle. This is the electron group angle. A bond angle, we need three atoms to define a bond angle. I'll talk about that in a minute, but that's not right. And so this is a trigonal planar electron group geometry, or EG, electron group geometry. Or electron geometry, however you want to say it. Now, if we do the fourth balloon, probably the easiest, we just bring it from the top. If we bring the fourth balloon from the top, it's going to push these three down. It's going to push these three down in an even amount. And we end up with tetrahedral. And so the electron geometry, tetrahedral, and the group geometry, not the bond angle. Bond angle, we need atoms to define bond angle, is 109.5. And so these are the scenarios that we're going to run into this semester. So we'll just take a look at them here individually. It depends on regions of electron density. Regions of electron density, that's a fancy word for how many groups of electrons are there. So what constitutes regions of electron density? What they're talking about is this. Regions of electron density equals a group of electrons. Now, a group of electrons you cannot break apart. You know, so for example, a lone pair we cannot split into two individual electrons. So let's say I have atom A. This lone pair counts as one group or one region of electron density. We can't split it into one and one. And so we don't count that as two. Does that make sense? The same thing, if I had a bond consists of two electrons. A bond, I don't split that bond up into two individual electrons. It's just one group of electrons. And so this would be like one balloon. The lone pair would be like one balloon. A single bond would be like one balloon. This would be bonded to atom B, let's say. Now, there is a slight difference in the lone pair versus a bond. There's a slight difference in the balloon size. Now, what do you think would be kind of a bigger balloon? Well, I kind of think that they'd be the same size balloon because both of them consist of two electrons, right? But if you think about this, they are the same size balloon, but one balloon is being stretched in a tug of war. Atom A wants that balloon, atom B wants that balloon, so the balloon's being stretched like this. Whereas the other balloon only belongs to atom A, so the atom A pulls in that balloon, right? If atom A pulls in that balloon, because there's no atom B pulling on that balloon, then atom A's balloon is a little bit kind of takes up more space, you know, around atom A. It's not being pulled towards atom B. Does that make sense? And so it turns out that this requires a little bit more space, more breathing room than a single bond. But we'll talk about that later. But essentially they're the same, you know, this one group. Now, if you had a double bond, let's say atom A were double bonded to atom B. Well, one thing is, I didn't talk about this, but double bonds are shorter than single bonds. Double bonds are shorter than single bonds because having twice as much negative charge density pulls in the nuclei closer together. Not only are they shorter, but they're also stronger. But it turns out they aren't twice as short and they aren't twice as strong. So there's something. It's because the electron density isn't totally crowded. And so these kind of take up more space. These kind of take up like space like a lone pair would, you know. So if we're trying to visualize balloons are kind of the repulsion part of it. Now, if we have a triple bond is has 6 electrons or 3 pairs. Wow, still don't have any drags. Check. I still have. Let me go into this room here just for a moment and grab an eraser. supposed to restock these rooms at night. All right. Now, a triple bond is going to be not 3 times stronger, but it's going to be considerably stronger than a single bond and a double bond here. So a triple bond should take up the most, because we're concentrating on that electron density there. The balloon's kind of like that. But all these are, this is one group. A single bond, we don't split up. Can we split up a double bond into 2 single bonds, separate single bonds? Turns out we can't split that up into two single bonds. And so a double bond is just considered one group. And a triple bond? One group. Now this is why I don't like electron pair. Electron pair means a pair of electrons, right? And so they're talking about, okay, if we have 2 electron pairs, 3 electron pairs, this is why they switched it. And rather than calling it electron pair, they used to call it electron pair. Regions of electron density, well, this is the number of electron pairs. Students will always get confused because the triple bond has 3 electron pairs, but it's only considered one group. And so this is all screwed up with electron pair, and I don't know why they continue to use the word electron pair because it's not a pair. But anyway, we'll continue here because it can even be a single electron. This is called a free radical. A free radical has an odd number of electrons, so we can't pair all the electrons. Odd number of electrons. It's a free radical. A free radical, even though it has 1 electron, is still considered one group. It's one group. And so the regions of electron density is equal to the groups. How many groups of electrons do you have? Okay, so we have some choices here as far as the groups of electrons go. So 2 groups of electron, linear. 3 groups of electron, trigonal planar. 4 groups of electrons, tetrahedral. So why did they do this? If we have 3 groups of electrons, it's trigonal planar. Why do we have 2 trigonal planars here? We have 2 trigonal planars here because of how many bonds we have. So for example, when we look at this molecule, we have 3 bonds here. When we look at this molecule, we have 3 bonds. No, we don't. We have 2 bonds because the double bond counts as one group of 1 bond. And so if we have 2 bonds, why isn't it linear? It's not linear because of this group. This group is a lone pair group. The lone pair group is going to push the other 2 groups up. There's no lone pair here. But the group geometry, the electron geometry is trigonal planar in both of these. See, this is trigonal planar electron geometry. This is a trigonal planar electron geometry. However, when we look at the atoms have a different arrangement. This is a trigonal planar arrangement of atoms, but this is what we call an angular or bent arrangement of atoms. So, either A, B, A, angular or bent. And so we have 2 geometries that we do for every molecule. One geometry is the geometry of the groups of electrons. The other geometry is what we call the molecular geometry, or MG. So we do an EG, MG for each molecule. The MG, we just look at the atoms. Like water. Water, when we think about the shape of water, we just think it's kind of like a boomerang shape, bent, call it, or angular. But in reality, it's got 2 shapes. One is the electron geometry. Water is actually a tetrahedral electron geometry, but it's bent or angular. And so let's take a look at something that's tetrahedral. This drawing is bad. This drawing is your standard Lewis drawing, but it looks like, what is the bond angle here? 90 degrees. Is that anywhere? The bond angle is supposed to be, and so for Lewis structures, they're drawn with total disregard of shape. If I ask you for a 3-dimensional drawing, then you have to draw totally different. draw like a 3D drawing rather than a Lewis structure, which is all flattened out. Here we have three groups. Two single bonds, or no, three single bonds and one lone pair. That's four groups, sorry. Here we have four groups. Four groups adopts tetrahedral. But this is not going to have a tetrahedral shape because when we look at the bonded atoms, it forms what we call a trigonal pyramidal shape. And this is like water. Water has two lone pairs and two single bonds, so it adopts tetrahedral electron geometry, but its molecular geometry is bent or angular. So this is like water here, bent or angular. And so we're going to look at these individually. Yeah, this is the kind of the rundown here of this. So here's some examples. When you draw methane, the Lewis structure for methane is going to look like this, because carbon likes to form four bonds. And so it looks like the angles here are 90 degrees, but the angles are not 90-degree angles. Not 90 degrees. When we look at this, what's the electron geometry? The electron geometry, I'm going to do in blue. The electron geometry should be, well, I have a single bond, single bond, single bond, single bond. So the electron geometry is tetrahedral. We have four groups. Then the molecular geometry, we look at the bonded atoms. And so for the molecular geometry, I'll do an orange here. Molecular geometry, we look at there's a bonded hydrogen, a carbon hydrogen, bonded hydrogen here. So the molecular geometry and the electron geometry actually match. So the molecular geometry is going to be tetrahedral as well. And so in a 3D drawing, you'd see it like this, but you're not going to draw this on paper. How are you going to draw this? Well, the way we're going to draw this is by doing this. Two in the plane at 109.5, one going in, one coming out. And we'll just attach the hydrogens there. Now, a bond angle is defined by 3. And so we have hydrogen, carbon, hydrogen angle. And the hydrogen, carbon, hydrogen angle, they're all the same at 109.5 degrees. Next one we're going to look at is going to be ammonia. Let's take a look at ammonia. NH3, we did the Lewis structure for this the other day. Nitrogen is where we put the extra electrons. Look at this. So when we look at the EG is going to be a lone pair group, a single bond, single bond, single bond. So we've got three groups of electrons. So the EG is four groups. Tetrahedral. Four groups. Three groups would be trigonal planar. Four groups. And the molecular geometry, so this is looking at bonded atoms. Bonded atoms. So if we look at just the bonded atoms, we see it's different. The electron geometry and the group geometry don't match. But this is not, the molecular geometry. The molecular geometry is not trigonal planar. It's not trigonal planar. The electron geometry, because of lone pair, is going to screw up the, I don't know, is that even visible? This is not visible. It's just right at the last. Trigonal planar. Here. And so to get the molecular geometry, we'll go ahead and first do this. Now probably the easiest position is if I have four groups, I need to have a tetrahedral arrangement. So let's put the nitrogen here, and then we're going to put the lone pair in the plane. And that means one single bond is going to come in the plane, one single bond is coming out, and one single bond is going in. And so if I just look at the atoms, what shape is the atom? Are the atoms arranged in? Well, the shape that the atoms are arranged in is trigonal pyramidal. It's a pyramid with a triangle base. So trigonal pyramidal is what we call that. And so that's shown here. Here we have 4 groups. However, when we just look at the atoms, the molecule has this shape. We don't pinpoint the lone pair because what was that principle? We don't pinpoint the lone pair's location because of the what principle? We can't pinpoint the electron position in the lone pair. Is the electron right here? And right here? It's anywhere within some kind of boundary, right? And we call that, we don't pinpoint it. We have a cloud, electron cloud. We call that because of the, what principle is that? I know you know what I'm talking about, but all scientists know this. Like, boom, they'll have it down because it's such a big deal. I know, but beginning chemists aren't going to have it down, but eventually you want to have it down. What was that principle? The Heisenberg uncertainty principle, right? Heisenberg uncertainty principle. So this is what. But can we pinpoint atoms though? Does a Heisenberg uncertainty principle mean that we don't know the exact position of the atoms? The only thing we can have is the probability of finding that atom? Is that the case? No, atoms can be pinpointed. Then you might ask yourselves, why can atoms be pinpointed but electrons can't? Aren't electrons just like particles or like atoms? Electrons, number one, they're a little different. Number two, electrons are not massive. Atoms are massive compared to electrons. So atoms can be pinpointed. So water molecule, no problem. We can see the shape of the water molecule using X-rays or whatever else. But we aren't going to see the shapes of the electrons. We can pinpoint the electrons at an instance of time, but we can't predict the next instant where it's going to be. Heisenberg's uncertainty principle is a bit more complicated than what I'm telling you, but you don't need to know all the intricate details of it. You just need to know roughly what it is. Right? But anyway, let's go on to water. When we draw the Lewis structure for water, we'll come up with this. Oxygen is the central atom, even though it's not the least electronegative, because hydrogens can only be terminal. And so here, we look at the electron geometry. The electron geometry, we got 2 lone pairs, and there's one other thing I want to talk about before I go on to water. I forgot to mention this. But what is the H and H angle here? The H and H angle. 109.5 degrees. That's what we predict. But the observed angle is 105. Actually, 107. The observed angle is 107. Do you know why? Yeah, exactly. Observed is 107. And what's happening is this. This lone pair is a bigger balloon and it pushes the other 3 in. If these other 3 get pushed in a little bit, it's going to distort the angle. And so the angle actually, because of the lone pairs take up more space. And the angle will be slightly less than 109.5. Actually, it's 109.47. So if we round it to 4 sig figs, it comes out to 109.5. If we round it to 3 sig figs, it comes out to not 110, it comes out to 109. Because if that would be a double round, double rounding would be 109.47 to 109.5, 109.5 to 110. No, we don't do that. We just round once. So 109.47 rounds to 109. So oftentimes you'll see this round. That was 109, not 109.5. So that sometimes that confuses people. Okay, now let's go to water. Water's like this, so it's going to adopt tetrahedral. The way I'm going to draw water is like this. I'm going to put the oxygen in the center, and then I want to put the bonded hydrogens in the plane. This is called in the plane. And that means I'm going to put electrons coming out. Electrons coming out of the plane, I'm going to make gold and black. Electrons going into the plane, I'm going to dot like this. So this lone pair sticks out of the plane. This lone pair goes into the plane of the board. Versus in the plane. If I have a set of dots like that that's in the plane, this is out of the plane, in plane, this is out towards you, and this is going in, under the plane or whatever. So, in plane, going in, going out. Anyway, the HOH angle should be what? 109.5 degrees because the lone pairs are distorting everything. It's not 180. A lot of people, I asked them what's the bond angle in Chem 4? You know how many people say 180? Lots of people say 180 because that's what I drew it as. It's 180. Doesn't it look like 180 to you? It looks 180 to me. You're right. This is a 180 degree angle. But are Lewis structures accurate? Three-dimensional structures? No. The actual angle is 109.5. Well, the actual observed angle is not. The observed angle is about 105.5 degrees. Let's say about 105 degrees. Why? Well, this is it. Do you see a little pattern here? Each lone pair kind of distorts the angle by roughly about what? Each lone pair distorts the angle or pushes it in by about 2 degrees. This is just rough. So we got 2 lone pairs at 4 degree distortion in the bond. 1 lone pair here about a 2 degree distortion in the bond angle. They call these wedge dash diagrams. I'm going to skip those other slides. We'll talk about this. NCl3. All right, let's do the Lewis structure for NCl3 and see what it comes out to. NCl3, we could do it the standard way, or we could just do it the Lewis symbol way. Maybe the Lewis symbol way for something like this, because nitrogen has 3 potential bonds, right, that we could form here. Chlorine has 1 here. And so obviously these can come together here, form a bond. We can just repeat this 3 times. And so looks like NCl3 will be something like this. Some of these we could just figure out like that, without having to go through all the steps. Other ones you'll have to go through all the steps to figure out. But does this make sense for NCl3? So what's the electron geometry? Tetrahedral. And so we got to get good at drawing tetrahedrons. For this, we want to draw this like ammonia. And so what we'll do is we'll put 1 lone pair in the plane, this is in the plane, and 1 bond in the plane. That means 1 bond is going to stick out and 1 bond is going to stick in. And so we'll throw in a chlorine here, a chlorine here, and a chlorine here. What do you predict the CL-NCl angle to be? We predicted it should be 109.5, but maybe distorted. What would you guess for the distortion? Well, 105 is too distorted. It's only one lone pair.
So that 107.
Yeah, maybe about 107. Distorted. Due to the lone pair. Lone pair taking up more space than a bonding pair. Okay, I don't like this drawing at all. What don't I like about this drawing? Yeah, I want to draw it the same way each time. That's okay, I could draw it that way too. Maybe I should draw it the other way. I don't know. You should draw it the same way each time. We could flip this 180. Draw. I could have drawn it like they drew it there. But yeah, you're right. This is all kind of tweaked. This is wrong as far as visually visualizing this. The angles are wrong here. This one should go above. This one should go below. If I were to draw it in the same way they drew it, I'm going to flip this 180. And so now the chlorine is in the plane like this. But this one coming out should go down, and this one should go above. Actually, we need models to see this. Let me see if I have the model here. So I'm going to remove this atom here. And so this would be like the lone pair. But if I orient it like this, so this is what I'm saying here. You know, lone pair in the plane, this is in the plane, this atom's coming out, this atom's going in. They're looking at it from down here. I usually look at it from kind of up here. So their perspective is kind of weird to me. What's going on with this? Here. But here, you could see it for yourself. All right, it doesn't matter if it's a multiple bond or a single bond. We just treat them the same way. So let's do C2F2 next. And so I'm skipping all the verbiage here. We're just going to continue because it's no different if we have double bonds or triple bonds. Before I do that, let's do something like CO2. CO2, yeah, there's fewer atoms. Yeah. And so when we come up with a Lewis structure for CO2, this is what I'm going to end up with. Actually, because how do I end up with that? Because carbon has 4 electrons, and then oxygen 6, another oxygen is 6, and so altogether we have 16 electrons. And then the steps. So this is the final answer. But the steps would be, okay, what atom do we put in the center? The least electronegative. And so we did this. And then what's the next step? The next step is to complete the octets to the outside atoms. We completed the octets to the outside atoms. Did I? And now we have 16 electrons, right? Except what doesn't have an octet? Carbon doesn't have an octet. So we have 2 choices. We could form 2 double bonds like this. We'd have to form, you know, carbon likes to form 4 bonds. It only has 2. Or we could form 1 triple and 1 double. And so if we form 1 triple, then we'll take 2 pairs off this oxygen and leave this one alone. Is this good?
No.
Why not? Everything has an octet. the symmetry, yeah, usually we like symmetry, but we don't always have to have symmetry. There are plenty of things that are not symmetric. Yeah, look at, what are the formal charges? The reason is not because of symmetry. The reason is because of, what's the charge on this oxygen? It's a formal charge. So let's count the electrons. We split these 50-50. So there's 1, 2, 3, 4, 5. How many is it supposed to have? 6, so it's short one. How about this one? 1, 2, 3, 4, 5, 6, 7. It's got an extra one. Is that tug of war sustainable? No, this is absolutely not good. Right? It's not going to happen. And so it's got to be 2 double bonds like this. Well, this is the structure we end up with. Now we go to the group geometry. What is the group geometry? We have 2 groups of electrons, a double bond and a double bond. And so the electron group geometry, or the electron geometry, is what we call linear. And the molecular geometry is looking at the bonded atoms. It's the same. And so the molecular geometry will be linear. And what's the bond angle here? The OCO angle is 180. And so double bonds work just the same way. We just treat them as a group. Same thing with a triple bond. You know, if we had a triple bond, it'd do the same thing. So let's do C2F2 now.
Professor, I have a question. That equation you just raised, will that ever form in nature? Or will that, is that even possible to make? Or will it just break apart right away?
It would break apart right away, or it would revert back. The electrons would, basically what would happen is electrons would go back. Now, will it form in nature? Not like that, but it's a potential way that electrons can be redistributed in nature. So let's say there's some kind of impact. Electrons might be redistributed like that, like this, for example. Boom, boom. And so let's say there's some kind of impact. It's got to absorb energy. Well, it can absorb energy in this way, or the electrons get transferred into an unstable state. And so in that sense, it can exist. In the quantum mechanics of things, though, all these kind of states exist, but they exist to certain percentages. You know, a very small percentage of these states can be mixed into normal states. But that's all the details. The quantum mechanics is more complex, of course, than what I'm talking about here. So, does it exist? Well, you know, it could be a part of some other bigger state, or it could be some excited state. So we aren't, but as far as CO2 goes, no. I mean, this electron's going to seek its lowest energy configuration.
Oh, right. Okay.
But as far as excited states go, yeah, maybe do that. There are a lot of species that don't live very long. Take a look at a flame. You know, inside the flame there are thousands. You know, well, I shouldn't say thousands, but there are lots of different species inside the flame. They don't live that long, and they're gone. Okay, let's go on to C2F2. How would you draw this? Well, carbon is 4. We got 2 of those. Fluorine is 7. We got 2 of those. So altogether we have 14.
You have 4 fluorine.
Well, 4 fluorines. All right. So that's 28. Plus 8 is 36. 36 electrons. Now, what kind of skeleton? Can fluorine ever go in the center? No. Fluorine's only single bond. So we'll put a carbon here. Then we might link it like this, carbon. And we know that carbon likes to form 4 bonds, so we might do like this to balance it out. We aren't going to get the full 4 bonds on there. So, how many electrons has that taken care of? That's 2, 4, 6, 8, 10. So we've got plenty of electrons left over. We've got plenty of electrons left over. Let's complete the octets to fluorine. This. We complete the octets to fluorine and then count how many electrons are left over. So let's do this here. So that's 8 here times 4 is 32. We use 32, we have 4 electrons left over. If we have 4 electrons left over, then, well, let's do this. We have 4 electrons? Let's see, 8 times 4, it's 32, so we do. So we can go like this, 1, 2. I think I must have miscounted. Did I miscount?
That's a double bond. A double bond. Or yeah, never mind.
I miscounted.
28, 30.
7 times 28, 32, 36. 8 times 4 is 32.
Where are we missing electrons?
We have too many electrons? We should have too many electrons.
Yeah.
That should be it. For some reason oh, you know why? I forgot to count these. I got 32, 34, 36. No, that's right. So I have 2 electrons, let's give 1 each to carbon. But does that give carbon an octet? No, so what we'll do is we'll just put those into a bond like this. Okay, now we're good. Now, when we do molecular geometries, we just pick the central atom. For CO2, it's easy. Central atom is carbon, and then we look at the geometry around carbon. For C2F4, it's more difficult because now we have 2 central atoms. They happen to be the same, but if they're not the same, what we do is we label these. So we'll call the first one carbon 1, we'll call the second one carbon 2. Like that. And then we look at it individually. So we'll look at carbon 1's geometry first, and then we'll look at carbon 2's geometry next. So looking at carbon 1's geometry, what is electron geometry? How many groups of electrons do we have? Carbon. Is it 3 or is it 4?
It's 3.
It's 3. All right. The double bond counts as 1. So we have 3 groups. 3 groups of electrons will want to adopt what electron geometry? Well, we only have 3 electron geometries. Is it going to adopt a linear? No. Is it going to adopt a trigonal planar? Yes. It's not going to be tetrahedral. And so this one, we'll just do a trigonal planar geometry like this. And then we look at the atoms. So we have a fluorine here, and a carbon here. What is the atom geometry? Here. When we look at the atom geometry, it is carbon 1. It's also trigonal planar. And so carbon 1 has a molecular geometry of trigonal planar. And its electron geometry is trigonal planar as well. We're most interested in molecular geometries as chemists. We want to know molecular geometry. So the electron geometry is usually not the end. Electron geometry is just a stepping stone to get to molecular geometry. So electron geometries people don't really pay much attention to. But you need to know it in order to figure out the proper molecular geometry. And so that means this. We're going to have an FCF angle, and an FCF FC angle. Now, we don't care too much about the atom size, like fluorine versus carbon, which one's bigger, which one's smaller. We care about the groups. Is it a single bond group or a double bond group? Which one takes up more space, which one takes up less space? That's usually what we worry about. But anyway, if we treat all groups equally, then the angle should be 120 degrees. And the FCC angle should be 120 degrees, all groups being equal. But a double bond takes up more space, it's a bigger balloon, and therefore, which angle is going to be compressed a little bit? The FCF angle is going to be compressed. And the FCC angle is going to get bigger. So this gets about 2 degrees bigger, this one gets about 2 degrees bigger. If this one gets 2 degrees bigger, this one's 2 degrees bigger, this one's going to get 4 degrees smaller. But this is getting too detailed. So what we're going to just say is it's going to be less than 120 degrees, maybe about 116 degrees. And so oftentimes you'll see books say less than 120. We're going to guesstimate 116. And this one's going to be greater than 120 degrees. We're going to guesstimate 122 degrees. If we want to get into the distortions of these things. If not, then everything's in the plane, you know. So the way we draw it, it's just like that, you know. Carbon 2 is exactly the same as carbon 1, so don't worry about it. But if it wasn't exactly the same, then we do another geometry determination. And so this molecule is flat. They say this is flat like a pancake. This is a flat molecule. Now, if you twist it 90 degrees this way, then it's going to stick out. This is what we call planar. It's all in the plane. Everything's in the plane. Lone pairs aren't done. Another thing we're interested in is polarity of molecules. Why do we care about polarity? Polarity tells us things. It gives us ideas about boiling point. It gives us ideas about solubility. This type of stuff. And so we care about the polarity. Let me talk about polarity. We don't need all these details here. We'll just look at examples. Yeah. So let's go straight to the examples. Polarity. So this is, how would you name this? CCl4. Carbon tetrachloride. Carbon tetrachloride has very polar bonds, but the molecule itself is nonpolar. So how can something with very polar bonds, because what is the most electronegative element on the periodic table? Fluorine. So fluorine's pulling hard for the electron cloud. Or chlorine. Chlorine is, you know, chlorine's like number 2 or number 3. Oxygen and the chlorine are close. Oxygen wins out because it's a little smaller. In Chem 1A, they have equal electronegativities. Electronegativity of oxygen is 3.5. Electronegativity of chlorine is 3.5. But oxygen has higher, even though it has higher because we're only looking at it 2 sig figs. Anyways, going back to these are very polar bonds. Do you see that? What's that symbol called? What's that symbol called? Delta. What does delta mean? That's a delta minus. What does that mean? Partial charge, not a full charge. And so chlorine, unfortunately, is not strong enough to completely pull the electron off carbon. And so they end up sharing, but they share equally or unequally. This is unequal sharing. But the cloud itself is going to be distorted towards chlorine. So this is what we call a polar bond. The carbon end of this bond is positive. The chlorine end is negative. So we got polar bond. This is a polar bond. This is a polar bond. In fact, all four bonds are very polar. All four bonds are very polar, and yet carbon tetrafluoride is non-polar. Why? And so this is pulling the electron cloud this way. And so it should be polar. But this is non-polar. And so carbon tetrachloride only dissolves in oils and that kind of stuff. Carbon tetrachloride does not dissolve in water. Water is very polar. And so this is insoluble in water. Why is that? Why that is it's hard to see. But we can see it with CO2. It's a lot easier to see with CO2. I don't know why they started off with this example, because CO2. Does CO2 have polar bonds? What kind of bond does CO2 have? Does it have ionic or covalent? Covalent. Is it non-polar covalent or polar covalent? Non-polar means they're about equal in strength. Are oxygen and carbon about equal in strength? What was that strength chart called? What was the name of that chart? Chapter 12. The name of this chart? Carbon 2.6, oxygen 3.4. Are they about equal? No. So this would be called a polar covalent bond. How about nitrogen and oxygen? Are nitrogen and oxygen about equal? That would be called a fairly non-polar bond. They're close. And so this is a polar bond. Now, which end would be negative, which end would be positive in the carbon-oxygen bond? Which one's stronger? The oxygen. And so oxygen is going to pull more of the electron cloud towards it. And so this gets delta minus. That means carbon is delta plus. This is the same. It's delta minus. The way we visualize it is like this. You know, the Heisenberg says we're going to have a cloud. You know, with probability. This cloud is going to be distorted like this. Do you remember I tried to show the distortion like this? It's not going to be symmetric. It's going to be an asymmetric cloud. The symmetric cloud would be like an oval or type shape here. It's being pulled there. There's more negative charge density over here. It's going to be more. It's not completely pulled over. If it's completely pulled over, we call that not a covalent bond. We call it a ionic bond. So anyway, this is polar. This bond is polar, and yet carbon dioxide. Does carbon dioxide dissolve in water? No, carbon dioxide does not dissolve in water. carbon dioxide is nonpolar. So how can this be nonpolar when it has polar bonds? Yeah. Right. They cancel each other out, essentially. And so, so we can have bond dipoles like this, but a molecular dipole equals the sum of the bond dipoles over 3 dimensions. And so what you have to do is you add up the bond dipoles over 3 dimensions. Well, if we add this up, then we have this one, they're equal and opposite. This is another way of representing the dipole. This is an arrow. The arrow points at the negative charge and it has a positive tail. You see these arrows are equal and opposite, so they cancel each other out. And so when we look at it, we take this bond dipole plus this bond dipole, and we end up with 0 bond dipole. So that's 0. It's a case where they cancel out. Now that's for linear. What about BF3? BF3, you know what I'd love to do with BF3? I'd like to make a double bond. I'd like to make a double bond with BF3. Why? Why do I want, I really want to make a double bond with BF3 because of boron. That would be a great fix for boron. If I could double bond this, then boron would be much happier. Why? If I could double bond this, boron would be much happier because it has an octet. And so boron would be very, very happy, but fluorine would be very, very unhappy. Why would fluorine be very unhappy? Well, it still has an octet. Did this fluorine lose its octet?
But now it's sharing instead of having one.
Right, now it's sharing rather than having its own pair, which means what? It's got a lot of pull. Fluorine's got the strongest pull. But when we analyze Lewis structures, we have to use a tool sometimes, and the tool is called formal charge. And so we look at the formal charges when we write up these Lewis structures to make sure they make sense. Because looking at it just strictly from an octet point of view, this is perfectly good. I could give you a rule. I already gave you this rule. The rule is that fluorine only forms single bonds, right? But that's a rule. Where did that rule originate from? So we got to look deeper into it. Where did that rule come from? Fluorine only forms single bonds. And the rule comes from this. If fluorine were to form a double bond, what would happen to its formal charge? What is the formal charge of this fluorine here? 6. It's supposed to have how many? It's supposed to have 7, so it comes up 1 short. What's the formal charge on boron here? It has 4. It's supposed to have 3, so that means it has an extra 1. And the sum of the formal charges is equal to the net charge. Well, plus and minus the net charge is 0. What are the formal charges here? All zeros. You see that? And so the situation here is that this fluorine is going to be very generous. This fluorine is going to give an electron to boron. Do you think that would ever happen? That would never happen. That would never happen. There's no way boron is strong enough. Is boron strong enough to strip an electron from fluorine?
Not a chance.
Not a chance. In fact, it almost looks ionic to me. In fact, fluorine should strip off all the electrons off boron. So this is not going to happen. And so we have that rule. Fluorine only forms single bonds. But anyway, fluorine's very strong. It's going to pull the electron density. All these bonds are very polar. This is delta minus, this is delta minus, this is delta minus. Almost ionic. These bonds are borderline ionic. Borderline ionic. This is very polar, the bonds are, but is this molecule polar? So the way, you know what people think of? They think of this. If you're stuck in the center here, and you have 3 fluorines pulling at you in these 3 directions, which way are you going to move? So if you're boron, 1 fluorine's pulling this way, the other 2 fluorines are pulling this way. Which direction do you move? You have 3 fluorines. This is like this. You're the carbon here. Oxygen's pulling you to the left, oxygen's pulling you to the right. Which way are you going to move? You don't move because these are equal and opposite, right? Okay, now we have 3 fluorines pulling you. You're boron. These 2 fluorines are pulling down, so are you going to move down? Are you moving down? Which way are you going to move? This is equal and opposite. Do you see it's equal and opposite? You're not going to move anywhere because you got these 3 fluorines pulling in at 120 angles. You're not moving anywhere. If you're not moving anywhere, this is called nonpolar. It's only when you move, and this is what, if you move, then there's going to be a molecular dipole. So let's do this. Let's replace 1 fluorine with a hydrogen. If we replace 1 fluorine with a hydrogen now, which way are you going to move?
Down.
You're going to move down. The hydrogen versus boron is about a tie, do you see? And so you're moving down, therefore this molecule is polar. And so we went from nonpolar to polar by switching it. And which way are you moving? You're moving down, so this is what we call the molecular dipole. The molecular dipole is the direction that you're going to move.
So, a molecular dipole would only occur during a polar bond.
Yeah, you have to have polar bonds. So we can eliminate a whole class of compounds, hydrocarbons. It doesn't matter the shape of hydrocarbon. You could have the weirdest shape, the weirdest geometries you want. They're all non-polar because none of the bonds are polar. The bonds aren't pulling, and we don't even bother. So all hydrocarbons are non-polar. So if we have non-polar bonds, we can't have a polar molecule. So anyway, carbon tetrachloride is non-polar, and that is because we have these 4 chlorines pulling, but which direction are we going to go? Nowhere, because they're equal and opposite. And so this is what we call spherical symmetry. So carbon tetrachloride is non-polar. However, if we replace one of those chlorines with a hydrogen, well, carbon and hydrogen, there's no difference, pretty much. And so this one's going to, the carbon's going to now be pulled towards 3 chlorines, which means the bond, the molecular dipole is towards 3 chlorines. That's what they're trying to show with this arrow here. It'll come out like this. Do you see it? If we replace 2 of the chlorines, which way is it going to move? It's going to move this way. Right? So the molecular dipole is moving that way. Again, carbon and hydrogen we can totally ignore. Even though they're writing delta pluses here, the difference, carbon is a 2.6, hydrogen is 2.2, it's only 0.4 difference. So it's negligible. These deltas should be written very small. But anyway, the carbon's delta plus for sure because this chlorine. And so which way is it going to go? It's going to go straight up. And so that would be the molecular dipole here. Now, these are all hydrogens. If they're all hydrogens, it doesn't matter the shape. So I can replace one of these hydrogen with a carbon, it makes no difference. And so this is why these delta pluses are misleading, because if I put a carbon here, then the carbon versus the carbon is the same. And so I have all these delta pluses. You think the direction would be here, but there's no direction. Because the difference is so small, it's negligible. And so I could have the weirdest shaped hydrocarbon, and yet it's still non-polar. Are we okay? Do you guys want a break, or are we okay? Just keep going and end early.
Just keep going. We're gonna have 12 minutes.
All right.
We got 12:26.
We get out 12:20 a day? All right. And so here we see CO2. CO2, polar bonds, equal and opposite. But H2O has polar bonds, but they don't cancel each other out. You see? H2O is highly polar. So which direction is it going to move? Straight out. This one's pushing this way, this one's pushing this way, it's going to move straight out. It's H2O. Why do we need polarity? We need polarity because of sort of physical properties. Now let's talk about organic and inorganic chemistry now. Organic chemistry, what do they say? Organic chemistry, study, research, and application of carbon compounds. Not all carbon compounds are considered organic. Like, for example, carbonate, like sodium carbonate. Sodium carbonate is considered inorganic. Carbon dioxide, is carbon dioxide considered inorganic or organic? Inorganic, but the distinction is not that big of a deal because there's so few. But anyway, the reason why carbon chemistry split off from the rest of the periodic table is because carbon can form 4 bonds. Carbon can form 4 bonds, which means it can form a wide variety. Not only that, carbon doesn't mind bonding to itself. Now, I told you I'm going to give you other tips and tricks. One of the tips and tricks is this. What was that molecule we were looking at, or ion we were looking at the other day? Some people do like bicarbonate like this. Do you see this oxygen-oxygen link? We've seen oxygen-oxygen links before, like this. Do you recognize this molecule, H2O2? It's hydrogen peroxide. What do you know about hydrogen? Is hydrogen peroxide stable or unstable? It's totally unstable. Hydrogen peroxide is unstable because of the oxygen-oxygen link. Oxygen does not like to single bond to itself. It's a peroxide bond. All peroxide bonds are dangerous. Peroxides are usually used in explosives, because they're quite dangerous. And so we avoid peroxide links like this. But what about a carbon-carbon single bond? A carbon-carbon single bond, no problem. The carbon-carbon double bond, no problem. Carbon-carbon triple bond, no problem. So we have no problem forming chains of carbon atoms. If we have one carbon atom in the chain, we call it meth. If we have 2 carbon atoms in the chain, we call it F3, 4, Bute, good. 5, fine. Like a 5-sided polygon. 5-sided polygon is called a pentagon. So pent is 5. 6 is hex. 7 is hept. 8 is oct. 9 is non. And 10 is deck. So we have no problem forming carbon chains. 1 carbon up to 10, even more. If you look at fats, 22 carbons, 26 carbons, etc. They're very long chains. Proteins, etc. And so this is why when we compare, there's such a huge variety of carbon compounds because of the way carbon can bond. And since there's such a huge variety, it becomes a field in itself, and that field is organic chemistry. So organic study carbon. Inorganic chemists study everything else. But everything else in the periodic table is actually a small number of compounds compared to organic. And so carbon, it's got the right size and right strength of bond formation. Look at the right size. Right size. Right side. The reason why oxygen doesn't like to bond to oxygen is because of the size. You know, the oxygen is smaller, and the two nuclei get too close, and it forms a weak bond. Right strength, the bond strength is pretty strong. They're stronger though, you know. Like silicon. Have you ever heard of like silicone? Silicone? Like silicone mats you can use in the oven, or silicone mitts. What do you think about that bond? That bond's strong because that bond can withstand a lot of heat. So there are carbon-based oils. When I used a vacuum pump, I didn't use carbon-based oils. Carbon-based oils would be like petroleum-based oils. I used silicone-based oils. The silicone-based oils I used were like 10 times more expensive than carbon-based oils for my pumps, but they're much stronger. You know, they lasted much longer before decomposing. Anyway, so that's kind of what it means. Formation helps form stable molecules, but weak enough to undergo reactions. Inorganic chemistry, chemistry of all element compounds except hydrocarbons and whatever. So carbonates, cyanides, oxides of carbon, a few other carbon-containing compounds are classified as inorganic. This is misspelling. Inorganic should be one word. So let's look at hydrocarbons first. We have alkanes that come up. Alkanes have no double and no triple bonds. These are hydrocarbons with all single bonds. And so alkanes, no double, no triple bonds. Alkenes, sorry, let's look at some alkanes. We'll look at some alkenes first, and then alkanes first, and then we'll look at some.
Can you go back to that?
Okay.
Right now.
Well, I just posted these on Piazza yesterday, but this is saturated. What does saturated mean? Saturated means no double bonds, no triple bonds. That's what saturated means. Unsaturated means you're going to find double bonds. And so, like, have you heard of saturated fats versus unsaturated fats? The only difference is that in a saturated fats, there are no double bonds. In an unsaturated fats, there are double bonds. And that tweaks the structure because when we're looking at a carbon-carbon bond, it tweaks the structure. Let me just show you really quick. When we have a double bond, then we put a little planar kink in the structure. And so carbon-carbon double bond is going to look like this. This is going to be trigonal planar, this is going to be trigonal planar. It's all in the plane, 120 angle. If that were a single bond instead, we'd show it like this. Let's try to show it like this. Do the geometry a little bit. Actually, let me not do this. Let me twist this around. I'll show it like a standard organic. So I'm going to draw it a little differently. And so if it were saturated, then this is the kind of the structural link we're looking at. If it's unsaturated, this is the structural link we're looking at. And so we can just see it really quick. The biggest impact comes from fats. So let's just take a quick look at saturated versus unsaturated fats. So what having that double bond does is it puts a kink in the structure. So an unsaturated fat will have a kink here because of this. The saturated fat will just continue on like a chain, but this is not three-dimensional. Let's look at a three-dimensional drawing or a three-dimensional structure of this. So so in organic chemistry, that leads to different physical properties. So saturated fat, since it's like this, do you see these are all tetrahedral? These black carbons? The blue are hydrogens. Black carbons are all tetrahedral. And so they can form a chain like this zigzag chain. Like that. So this is butter here. This would be olive oil here. Olive oil is unsaturated. It's polyunsaturated, so that means that poly just means there's more than one double bond. So polyunsaturated fat like olive oil, it doesn't pack together nicely. If it doesn't pack together nicely, it's actually a liquid. A butter is a solid because these pack together. So here's one fat, here's a second fat molecule. They pack together nicely. These two don't. And so here again, saturated versus unsaturated. This is a better definition than our books. I like this definition. Saturated, single bond between all carbons. Unsaturated, double bonds between one or more pairs of carbon atoms. That's a much better definition than our books. Our book's definition. Well, I guess it's the same. A saturated hydrocarbon containing only single bonds. All right. Reading too much into it. So these are all saturated here, but saturated versus unsaturated, we don't even care about that when we're talking about fats anyway. Normally we don't talk about it. We talk about alkenes. Alkenes have all single bonds. And so how many carbons? Well, the blacks are the carbons. You see, this is tetrahedral. What's this carbon? Hey, that's tetrahedral too. Two in the plane, one coming out, one going in. Tetrahedrals will always two in the plane, one coming out, one going in. Two in the plane, one coming out, one going in. So this is why I drew it like this. Two in the plane, one coming out, one going in. Two in the plane, one coming out, going in. And we can zigzag them like this. And so this is it. How many carbons? 4, so we call it bute. Are there all single bonds? Yes, we call it butane. Now N stands for normal. Normal butane. How many carbons? 4, but this is different. This one is called isobutane. Iso means it has this little fishtail. So isobutane has this little fishtail here, or we call this 2-methylpropane. 2-methylpropane. We do a 3-carbon chain and then throw a 1-carbon unit on there. This one's called, how many? Pentane. This one's called iso because it has a little fishtail.
Those are gases, right?
No, pentane's a liquid. Butane's a liquid, but it's a highly volatile liquid. Have you looked at a butane lighter? Butane lighter is liquid on the bottom, but it volatilizes, it vaporizes into gas. Propane's a gas. Actually, propane's a gas under normal conditions, but when you put it into a propane tank, it's a liquid. Have you ever shaken a propane tank? It's filled with liquid. But it's a very volatile liquid. Evaporate. This one is called neopentane. Neopentane is this spherical ball-like molecule. Neopentane. It's also called 2,2-dimethylpropane. And so if you take a propane and then add a methyl, which is one carbon, and add another methyl, which is one carbon, that's called 2,2-dimethylpropane. That's it. Which would be more of its common name.